Today we're going to be talking about how to reparametrize the curve with respect to arc length, and in this particular problem we've been given the vector function r of t is equal to 2ti plus the quantity 1 minus 3t times j plus the quantity 5 plus 4t times k. And we've been asked to reparametrize this curve with respect to arc length from the point t equals 0, the point where t equals 0, in the direction of increasing t. And reparametrizing the curve basically just means that we are redefining the curve in terms of a different parameter. So right now our vector function is defined in terms of a parameter t. So we have this vector function r, it's defined in terms of the parameter t. We want to define it in terms of a different parameter, and we'll use the variable s as this additional parameter for arc length. The reason that this is useful to us is because arc length doesn't change no matter which coordinate system you're operating in. So it's kind of a standard that we can use, and if we parameterize the curve with respect to arc length, then we know that we're going to have a function that we can work with across coordinate systems. So sometimes this can be useful with higher level math. And what we're going to do to reparametrize the curve is first we need to find arc length, right? We're reparametrizing with respect to arc length, so we need to go ahead and find arc length. And remember here we have this arc length formula. Sometimes you'll see dx over dt written as f prime of t, dy over dt written as g prime of t, and dz over dt written as h prime of t. Of course, those formulas just mean the same thing. This is just Leibniz notation, and I like to use this formula more than the other one just because dx over dt is more explicit in terms of we're taking the derivative of our equation for x in terms of t than just f prime of t. So what we need to do is pull out of our vector function our parametric equations. So of course we're going to take the coefficients here on I, j, and k, so just everything here in front of I, j, and k, and we're going to set those equal to x, y, and z respectively. Those are going to be our parametric equations. So we have x equals 2t, y equals 1 minus 3t, and z equal 5 plus 4t. Now what we need to do is find derivatives of each of these functions with respect to t. So we'll say dx over dt, the derivative of x with respect to t, is going to be equal to 2. When we take the derivative of 2t, we just get 2. dy over dt, we're taking the derivative here of y with respect to t. The derivative of 1 will be 0. The derivative of negative 3t will just be negative 3. So we just get negative 3 there. And then dz over dt, the derivative of z with respect to t. The 5 is going to go away. The derivative there is 0. The derivative of 4t is just 4. So we get the derivative. Now we need to plug these values into our arc length formula. The only thing that's tricky here about our arc length formula is not plugging in these derivative values, but dealing with our limits of integration a and b. So normally if we were asked to find the arc length of a vector function, we would just be told to find it on the interval, let's say 0 to 1 for t. We'd be told that t is greater than or equal to 0 and less than or equal to 1, and we'd plug in our limits of integration. But here all we have to go on is the fact that we are reparametrizing the curve from the point t equals 0 in the direction of increasing t. So we say t equals 0, that means that's going to be our lower limit of integration. In the direction of increasing t means that positive t is going to be our upper limit of integration. If we were told to reparametrize the curve with respect to arc length from t equals 1 in the direction of decreasing t, our limits of integration would be 1 and negative t instead of 0 and t. So we have here 0 and positive t from t equals 0 in the direction of increasing t, or positive t. And now we just plug in our derivatives. So we get the square root of, here we'll plug in dx over dt and get 2 squared. Then we plug in our dy over dt, so plus negative 3 squared, and then we get plus 4 squared when we plug in dz over dt, and of course we want to keep our dt outside of our square root sign. So when we simplify this, we get that the arc length is equal to the integral from 0 to t. Now when we take the square root here, we get 2 squared, which is 4, negative 3 squared is 9, positive 9, and 4 squared is 16. So here we're going to get 29, so we just have the square root of 29 dt. Well, the integral of the square root of 29 is just the square root of 29 times t, and we're going to evaluate that on the interval 0 to t. And this becomes really convenient because the limits of integration 0 to t from t equals 0 in the direction of increasing t, that's the interval you're going to see most commonly when you're asked to reparametrize the curve. And as you can see here, when we plug in our upper limit of integration t, we're plugging in here for t, so basically we plug t in for t, we still just get t, the same thing. Then we subtract our lower limit of integration, so square root of 29 times 0. Well, this is going to go away, and we're just left with square root of 29t, the same thing that we had here, right? So if your limits of integration are 0 to t, you know that you already have here your arc length. You don't really even have to plug in the limits of integration to find the arc length function. So now that we have this arc length function, remember we said we wanted to use the variable s to define arc length. So we'll say s is equal to square root of 29t. The reason we want to use s is because it's a parameter value like t, so we just use this lowercase s instead of a lowercase t. We want to go ahead now and solve this equation for t, because what we're going to do is substitute whatever we get for t into our vector function wherever we have t here. So solving this for t, we divide both sides by square root 29, and we get t is equal to s over square root 29, like that. We have a value now for t in terms of s, so we've reparametrized the curve. When we substitute s over root 29 in for t, now we'll have a vector function in terms of s instead of in terms of t. So writing our final answer, here's what we're going to get. We're going to get r of t of s, and the reason we write it like that is because here we have a value for t in terms of s, right? So t in terms of s, and we've plugged that into our vector function r. So we have r in terms of t, which is in terms of s. So we say r of t of s is equal to, and now plugging in s over root 29, and it's actually typical to bring this s outside of a fraction if you end up with one. So we want to write this as 1 over root 29 times s. That's the way you'll most commonly see it. So plugging in here, what we're going to get is 2 over root 29 times s, and then I here, so we get the I. But we just plugged in 1 over root 29 times s. We plugged that in here for t. We'll do the same thing for the coefficients in front of j and k, and we're going to get plus 1 minus 3 over root 29 times s times j, and then plus 5 plus 4 over root 29 times s times k. This is now our vector function defined in terms of the parameter s instead of the parameter t, so we've reparametrized the curve with respect to our arc length function from t equals 0 in the direction of increasing t.